Greetings. Welcome to Computer Models of Language Representation and Processing. I am Professor John Lindstedt. I'm a professor of cognitive science, and I'm going to be your guide on this stroll through the concepts of how we can make computers chop and screw language to make some interesting stuff happen. So, this is the course overview. We're going to talk a little bit about what's coming, but also sort of the heart of the course. What are we doing here? What's the purpose of these of all these techniques that we're going to be learning? So, to start off, I'm going to show you. Let's just get into an example of how you, a human being, might take language that is handed to you and make sense of it, do something with it, right? What if I gave you this sentence? If I spoke this sentence out loud to you: design an armchair in the shape of an avocado. The first question is, what do you do with that, right? Even setting aside the destination, right? You already know what you're gonna do. If I gave you this command, you would start to do certain things, right? But you probably first say why, but let's assume that you're a designer and this is sort of your job, right? So I give you this sentence, and you kind of already are piecing together where you would go with it. The question is, how do you do that? What are you doing to make sense of this string of symbols that I've just hurled at you, either by way of text or voice, and you caught it, and now you're going to do stuff with it? First, right off the bat, we can think about, you will start to kick in some kind of syntax parsing, right? You'll immediately try to break this up into meaningful parts of speech, right? Then you'll start to look at those parts of speech, and you're going to come up with certain relevant bits of information. For example, there's an action here. There's a call to action. Design, which you might translate to draw or sketch. There's some objects mentioned that you might need to pull up memories of: armchair, avocado, things that you need to visualize somehow, make use of. There's a property here, shape. There is a sort of a translation here, and now we can also look at, I'm going to have to do some work mapping the concept of an avocado onto an armchair. The specifics don't matter too much, but the idea here is that you have taken this arbitrary string and turned it into something you can act on. So you might start to act on it. You might sketch out an avocado and label it avocado. You might sketch out an armchair, start to think about these things, and you would name that armchair. Now, what else might you do? You might break this into distinct concepts, like, what are the pieces of these things? Avocados have pits, they have skin, they have the fruit, the meat of the fruit, right? What's an armchair got going on? It's got some legs, it has a seat, it has the base, it has the back, arms, it has fabric on the outside. So now you might also start to try to map some properties onto each other. How do I make a connection between avocado and chair that will help me to design a chair that has properties of avocados? We have to have some kind of mapping. So maybe the skin of the avocado, or maybe the meat of the fruit, might map to the fabric, right? We might start to change the colors of the fabric. The pit. What are we going to do about the pit? How do we want to represent the pit? Maybe that's the cushion. Maybe that's a pillow a throw pillow that we put on there. Then there's another element here: the things that don't map, the things that can't map so easily. The legs, for example. There's not really anything in an avocado that resembles a leg, so maybe that's just something we leave on the side. We just say chairs are going to have legs, don't need to worry about it. You also might start to pull apart the colors that you know that an avocado has and try to apply them onto the chair, right? So, sorry, I've thrown you into this role as a chair designer. Don't worry too much about it. You will not be graded on your chair designing skills. what's the point of this exercise? We are looking at the idea of how, so language comes in, something happens, and then actions can be taken. Sometimes those actions are designing a chair. Sometimes they are just you sort of thinking more, right? Either way, you've chopped up language. You've processed language as it came in, and you have turned it into something useful, some kind of internal concept, some kind of internal model that you can then use for other things, right? So that's the idea that we're getting at with this course, is we're taking language and we're going to chart how it can be formed, right? How it can be transformed, how it can be processed, how it is represented, how your internal models might look. So, language. Language is this sort of currency of the mind and social interaction, right? We transmit ideas through the medium of language. It comes in various forms, right? You can read text, and that is language. You can speak sounds, and that is also language. So the idea is that there is a common feature. There is a common set of symbols, and there's many mappings toward them. In fact, when we speak a language, that's a funny thought sometimes. You think about how humans turn audio signals into things that are a little bit more symbolic. How do we do that? We take language in and we turn it into some kind of internal representation that matters to us. Here's a bit. All You Need Is Love. The song by the Beatles, right? That's a meaningful thought. And it's audio. It's sound waves. It comes in, and it's meaningful enough for this person to have framed it, right? They love it. Sorry, if you hear a clang, that's me setting down a coffee cup. So, yeah, this is the idea. This is sort of where we're going here. We're trying to get at, we're not going to focus on the concept of love through language, of course, but it's more about how can we capture some of the processes of transforming language as it comes in, and not necessarily from audio, that's sort of a different thing, but natural language that humans use. How do we take that, break it up, and do interesting things with it that resemble humans? And that's where this is a computer-based course, right? So we will be doing all of that through the use of computers and computing processes. So let's break the course title down a bit. That helps to sort of guide what we're doing here. The title of this course is Computer Models of Language Representation and Processing. Ugh, but there's so many concepts crammed in there. What are we talking about with all these things? What are models exactly? What are representations? Or what is the concept of representation? What do we mean by processing? What are we talking about language? What is a computer? What are we doing here? We'll get there. Let's break each of these apart and talk about them. So first, let's get a sort of a gut understanding of what we mean by representation. Representations are the reduced form of something when it is stored somewhere for later use in perhaps a reduced capacity. It's a little tough to pin down because it's sort of anything is representation that might stand for another entity. So what pins this down a little better is think about computers and humans. How do we internally represent the outside world? There's a few different ways you can tackle this. So consider this. What is this? That's a cat, right? That is an image of a cat, which in itself is only a representation represented on this computer in this video of the real world animal that lives and breathes and eats and does stuff, right? That is a representation of the cat. What are other representations that fit this? The letters CAT written down, right? That is a representation. Those are symbols that represent the concept of cat. Might not be this specific cat, but same idea. As we just talked about, sound waves can also, in the same way as the written symbols, represent cat, right? The spoken word cat. Or you could do an icon, right? A reduced symbolic form that doesn't rely on letters and sort of the abstract language stuff, but it is still a representation. It still communicates something, and it still can hold sort of a pointer to the real thing, right? A little bit more maybe perhaps not abstract, a little bit more interesting and complicated. Your brain does representation. When you think about a cat, the concept of a cat, the properties of a cat whom you may know, something in your brain, some pattern of neural activations is lighting up. That is an internal representation of cat. It perhaps isn't perfect, and it's a little bit noisy. You know, your brain is doing all kinds of stuff in there. But that is also a representation. Also, to kind of circle it back to this first point, this image of a cat, how is that represented? How are we holding on to that information internally? That's all ones and zeros, baby. That's the way computers represent many, many things, right? So, okay, this is a very fundamental concept, the idea of representation. How do we take something real and hold it in a reduced form that we can use later to point to that thing, to think about that thing, to talk about that thing? So that's representation. We can also talk about processing. Processing. What do we mean by that? That is the concept of how entities like, say, objects in the real world, or perhaps information itself, are transformed and transmitted, right? So what are some processes that we can think of? Cooking, for example. That's a process that turns ingredients into meals. You are taking steps, you are changing the properties of the various items. You might be cutting them into smaller parts. You might be changing their heat and allowing another chemical process to take shape, chemical and physical process. Processes can be composed of lots of other processes, right? So we process things. So another element is reading. A process that turns written symbols, so things on the page of a book or on this slide itself, into thoughts and concepts, right? In the same way that you have to chop up the onion to make use of it in your recipe, you have to transform the words that are coming in into some kind of, as we talked about, representation, some kind of internal version of itself that makes sense to you and you can use in other ways. Okay, so those are some basic units. But that's the idea of representation as sort of a form and processing as sort of a method. And so let's step up a little bit into what is a model. So models are, yet again, these are all fairly abstract, very broad places that we're looking at here. But any reduced form that will capture a relationship or some kind of structure from the real world. You can think about a model plane, say this is a reduced form, right? It is a It is a plane. It still has all of the same moving parts. It doesn't have the engine, of course, but it has most everything else does what it's supposed to do. You turn the little wheel on the plane, it moves not the wheel, I guess, whatever. Often a high fidelity model on a reduced, in a plane model will actually be able to turn its rudders and such, right? The connections between things in the structure of that plane, in the way that it acts and behaves in the world, are preserved. And that makes it so that you can look at it, you can analyze it in a reduced capacity. It helps you make sense of the real world thing, but in a reduced form. Anytime you look at a weather graph, a weather radar, it's attempting to make predictions. It's attempting to capture all the crazy moving parts of how weather systems interact. But it's not the real world, right? It is trying to make sense of these chaotic moving pieces and predict, hey, I think the hurricane is going to hit here, right? That's a model. Those are models that help say, hey, these are all the things we understand about how weather moves around and interacts with each other. And this is what we think could happen, right? The ability to simulate and make predictions about the real world. And we can also talk about neural models, right? Models of neural networks that behave as close as we can get them to neurons, actual neurons that you have in your head, right? That is also a model. It is a reduced form. It is not a bunch of actual neurons. It's a bunch of simulated neurons that behave closely to how we think they do. Models are great. Models are useful in science, but models are also useful inside your head. You keep track of some kind of relationship from the world, and you wield it to make sense of the world around you. Now, processes and representations are involved in models, and models are a form of representation as well. These are all overlapping concepts. Just trying to get you into the baseline understanding of what all these basic concepts are. Jog your memory, bring you back up to speed. Okay, now I said this kind of in jest, but let's break out language as well. What do we mean by language when we're talking in this course? Primarily, we're talking about the symbols and the forms that you use to communicate that information. And sometimes it's often to other people, but sometimes it's to your own self. You are using language internally. Sometimes you think in terms of language, it's thought. And language is these complicated, dynamic way of engaging with information in a symbolic fashion. It involves, so it's a sort of the natural thing we're trying to capture, right? And it will involve representations, processes, and models to understand it. Now, how are we going to do that? With computers, right? Our good old friend, the evolved universal Turing machine, the jack of all trades, right? These are the devices that we do everything information, all things information in the modern world that were happening on computers. You probably have a bunch of them, right? You probably don't even think about how many you have. Oftentimes your toaster has a computer inside of it at this point. Your pot that boils your water, your microwave. They all are forms of computing machines. Now, they're not all universal Turing machines, but they essentially, we're getting to that point. You know, think about a Raspberry Pi. Okay, why am I babbling to you about computers? Computers are our best way of capturing these sort of abstract processes right now. This is the way we take these machines that are really good at processing information, moving it around, transforming it, and we try to capture processes like comprehending language in a computing setting. So because computers can handle information processing in ways similar to humans, that makes it great for modeling human-type processing, but they also do things way better than us, too. They can be a lot faster and more powerful at certain things. We're still pretty great at things like pattern matching, so don't worry, they haven't eclipsed us yet. But They're getting there. So, okay. Blah, blah, blah. Many, many different definitions here of sort of basic concepts. I'm sure it's review for some of you, but hopefully it's just getting you locked back into what we're doing here. And let's put it all back together and get it. What the heck is this course about? So, when I say this course is about computer models of language representation and processing, what I'm saying is we're asking this question: how can we take various models of our understanding of natural human language, the ways we represent it and process it that are known to us, and get a computer to do them in a similar way? It's sort of the computer is our playground for how we better understand language. And also, it's our workbench for building something that can do interesting stuff with that language. So, as we go on, we will discuss how this helps us better understand language all together, like as a concept, as a natural phenomenon that humans do, but also how it empowers computer to do some pretty wild things. So, let's talk about the course plan. How are we going to achieve this? Well, to start, we're going to start with a Python programming primer. Basically, that we're going to learn, you're going to learn how to use a programming language. Obviously, some of you have touched on things like Java or JavaScript. Python is the one that we're choosing for this course, and I'll explain why shortly, and don't worry about it. We'll get there. It's a gentle introduction. But the idea is you need to have some programming information processing tools in your belt before we can start messing around and doing interesting stuff with language specifically. Then, after we get through that primer, and these all overlap a bit too. I'll explain an interesting concept, and then we'll do some programming around it, that kind of stuff. So, next thing we'll do is explore a lot of techniques and tools and applications in the realm of computer models of language. We'll see how some of them work. You'll make them yourself. And it gets pretty fun. It's honestly pretty funny. Models that produce language are pretty weird and sometimes goofy, and that's great. It's fascinating. And then finally, around the 10-week mark, about 2/3 of the way through the class, you'll start on your final project. It will use the things that you've done, and you'll pick something that you want to make, that you want to build of your own volition, that you want to, say, tackle a problem that you're curious about. Don't worry. You'll start to see what you're capable of doing in the course, and then you'll figure out what's interesting about that to you as we go. One hopes. So, let's look at each of these. Python programming. What can you expect here? You're going to learn some core skills. The idea is we're going to go through some basics of the Python programming language. Lots of little stuff, like how to write and run scripts from scratch. In fact, that is something that deserves a little focus because people often think, oh man, that sounds daunting. It doesn't have to be. It can literally just be a text file that you learn how to run from the command line. And I'll show you how. We'll get into some fundamental programming concepts, like legitimately programming. This will be review for many of you, but it's also just a good thing to get a little exposure to if you've been avoiding it. So, how do things like variables work? Objects. How do you branch, make if-then statements, right? How do you loop around and do things repeatedly in your code? And that's it. I mean, those are the fundamentals of programming. So you'll get some re-exposure to that, and then or first time exposure, some of you, of course. So then we'll also talk about some specific ways of how working with text is unique. Different tools we can use for splitting up text, chopping it into these like usable tokens and words and all these various things. And I'll also show you how to import packages, external packages, into your Python programming toolkit, so someone else who did something way better than us, we can pull their work in. That's the open source way. That's the way you can really interact with the programming world outside of yourself. So that's the idea. Again, we'll start with a sort of a gentle slope upward into the concepts of programming with Python, and then you'll develop all those skills as you use them in the assignments. So I want to take a minute to do some shilling for Python's sake. Why am I choosing Python to teach this in? So some of you have been exposed to Java and C# already, things that are more enterprise programming languages, right? In the business world, a lot of companies use these things. They are great for optimization. They're easy to scale up. They have compatibility with all these existing systems in the world. Here's the thing. Regular folks use Python. At least this decade they do. And what do I mean by regular folks? Well, even scientists, my kind, we're not hardcore programmers, but we need to know how to program things. We need to be able to whip up information processing tools on a whim when we need them. So scientists, hobbyists, just people who like making code for fun, people who are involved in hacking communities, whoever. The idea is that if you're whipping up a program on your own, at home, on your own time, Python is really the language that's going to hit the sweet spot between power and ease of use. And because it is much cleaner to read and interact with in many ways than a lot of these other ones. So Python is powerful. It's super well optimized for small scale things that you're going to be using on the everyday scale. And it has tons of community maintained open source packages. It's really well documented online. Tons of people use it, right? That's a huge benefit because you're never on your own, A lot of people approach programming, teaching programming and understanding programming as though you need to be a perfect computer yourself. That ain't the case. There's always going to be Stack Overflow and StackExchange.com where they will have people, millions of different use cases and errors and questions that have been solved 1,000 times before. So you are never alone when you're using a well-adopted language like this. It's clean to write and easy to test. You'll see that using the interpreter is great for just screwing around, debugging, learning things, exploring. And ultimately, for your sake, knowing a good scripting language like Python will help you get things done, right, with programming that you maybe never would have considered in your life. So I'll stop harping on this, but the idea is that Python is a great, just like everyday programming language for a normal human, right? Not just for your business purposes. So I hope that I can give you some tools that'll help you think of this as like something good that you can always turn to, and not just say something you learned for a class. So, okay. So that's what we'll do. We'll get Python up and running in your brains and how to sort of tackle it. And we'll also, from then on, after those couple 2 weeks, we will get into exploring interesting techniques used in language modeling and producing interesting models of language in computing settings. So, what are a few of these? Things on the roadmap. Not sure if these will all be the same by the end, but these are the ideas that we're aiming at. Pattern matching with regular expressions. Regular expressions are this powerful tool you can learn to use. We'll talk about Engram models of language, so this sort of step-by-step statistical understanding of language as a string of text. We'll get into vector semantics. So how do we represent semantic relatedness in something a computer can handle? It's a little bit tricky, a little bit interesting. We'll see what we can get there. And then we'll also take some time to talk about neural network models of language and some of the science behind those and things that have been developed for that. And potentially more tools or alternative tools to these that we've discussed here. Well, let me pull apart some of these ideas, though. Give you a little preview of where we're heading. So first, we're going to get into a well-known tool for moving and pattern matching and finding things in text, regular expressions. You may have heard of these before. You may have even seen them in one of my other classes. But the idea is that these are a common tool that exists in many programming languages. So if you learn them in one, you will learn them in more. For rapidly finding patterns of text in a long string. So if we think of language as a long string of letters and words and sentences and all that, regular expressions are a great way to find things within that fit certain criteria. We will talk all about that. You can sort of see a little breakdown of one little regular expression here. And yeah, so this is sort of a way that a computer can analyze and find different features within a string of natural language. Another way that we will think about natural language is with Engram models of language. So these are models that they take language, a long string of language, and they break it up into lots of little tiny substrings. And the idea is that you can, one way to use this kind of analysis is to say, well, given one word appears, what is the likely next word to appear? And you can create these models that sort of probabilistically choose the next word just like this. This is exactly like on your phone, you have that little predictive text tool, right? That's this. It just says, hey, the last word you typed, you typically type something else after that. Here it is. It's not always right. And in fact, you know how dumb those things can be. But that's a model of your language. The predictive text on your phone contains a model of the language that you typically produce by typing. So we'll get into how those work and getting to use them for different things. We'll also talk about vector semantics. So this is about ways that we can turn word concepts, which are nebulous, interconnected, super interesting inside of a human brain, but kind of find a way to make them at least mathematically relatable to each other in a computer, right? So it's about assigning numerical vectors to words and concepts, and then being able to tell how far apart they are in a virtual vector space. We don't worry too much about that for now. This is what we will cover in the later lectures, but just a preview of what kind of things we'll talk about. And finally, the last one that we're sort of putting on the roadmap is neural network models. So examining how architectures like our brains might handle processing language using neurons. Now, this isn't to say that we're going to cover literally exactly how brains do all language, but it's more about if you're bound by having neurons as the basic unit, the neural network type neurons, the simulated neurons, how can you apply that to things like language? So taking an input string and being able to predict what the next word is using a neural network model instead of a sort of more of a symbolic model like we've talked about in the past couple slides. So that's the preview. These are the kinds of places we're going to go. We're going to learn a lot of cool stuff on the way, and that's the map of everything up until. Have you heard of GPT-3? It's starting to make headlines here and there. It's an iterative thing. A couple years back, GPT-2 was the fresh thing, and now we're on to version 3. It's Generative Pre-trained Transformer version 3. Okay, that's the most generic name you can think of for this thing. But that's because it's supposed to be very general in its abilities. What it does is it's this huge, complex, evolving software system that does great stuff matching and processing human natural language. So it is a complex, a super complex model of language. and that model has 175 billion parameters. It's the largest language model ever created. And what is it good at? Well, there are applications that do all kinds of things. It can take language and produce language. It can take language and produce programming language content. And it can take language and produce images even. So let's look at some of these examples. Language to language. This is a project that in its raw form takes GPT-3 and just feeds it some language, and then someone gives it a prompt and it produces language similar to the first. Let's look at an ancient text by Jerome K. Jerome on being idle. Now, this is a subject on which I flatter myself I really am au fait. The gentleman who, when I was young, bathed me at wisdom's font for 9 guineas. Okay, we don't need to focus on it forever, but the idea is get a flavor for how this text is written, how this person writes. They're pretty floral. They have a lot of flourish, right? They're colorful in the way they approach this. They're also a little ancient. This seems like maybe, early 19th century, I suppose, or 20th, whatever, 19XX. So this is the text that was fed into GPT to say, hey, learn how this language is produced. Okay. Then along comes Twitter programmer person, Mario Klingerman. And what did he give this? All I seeded was the title, the author's name, and the first it. And the rest was done by GPT-3. What did it produce? It produced this entire article about the importance of being on Twitter by Jerome K. Jerome. So, not true. He's gone. That is not. He did not write this. Jerome K. Jerome did not write this. London in summer 1897 about the importance of being on Twitter. Let's do a little reading. It is a curious fact that the last remaining form of social life in which the people of London are still interested is Twitter. I was struck with this curious fact when I went on one of my periodical holidays to the seaside and found the whole place twittering like a starling cage. What does that even mean? I called it an anomaly, and it is. Okay, that was kind of coherent. You might have seen, in your life, you might have seen some fun like chat body things and language nonsense. Oh, a computer wrote this thing, and it's usually funny. This is pretty good. Like it's actually coming up with coherent thoughts. It's even capturing Jerome K. Jerome's critical nature and sort of florid speech patterns, right? This is a whole article written about Twitter in the sense of someone who was living in 1897. And you can just keep producing articles. It just keeps going on being an automaton, on wireless fidelity, on giving unsolicited advice, on social distancing, on having a choice. These are all fabricated articles that have captured something about how Jerome K. Jerome produces language and simulated it, created it. They have now written articles in his style over and over, as many times as it needs to. That's the power of something as complex in this realm as GPT-3. We can screw around further. We can look at how it changes language into programming. Here's a quick little video that shows, hey, design me a little web interface layout based on what I tell you, right? So it's still taking a human being typing, just normal language, and it will process it and comprehend it and be able to do something with it. So give me a button that looks like a watermelon. Takes that information, spits out HTML. large text that says, "Welcome to my newsletter," and a blue button that says "Subscribe." Screwed up, forgot to specify a color, so it's in red. It did it. It produced the text, HTML text, that produces this. And we'll watch it make the rainbow colors, right? A couple minutes here. A lot of fun stuff. It goes on. You can find this. This one's complex. I'll let it run this one. Table of richest countries in the world with columns, name, and GDP. It's able to go find that information and put it into the table. It's able to comprehend some of this stuff. He does have to fix it. It's a little bit busted, but table, come on, render it. And the T-body, there it goes. There it is. The system just ran out and found that. We're gonna go on. So that actually was the first iteration. This project has evolved. Here's Source AI. It is a project designed to allow you to convert your human request into any programming language. So say it's going to create something in Python. A program that tests whether a given number is prime or not. Well, there it is. That is a script in Python that you could sit down and write that helps to, it will solve this question for you. That's wild. This is like heavy duty software development that is happening, on the cutting edge, right? I wouldn't necessarily trust these auto-generated things to the extent that they, just deploy it. It's fine that the computer wrote that code, right? But it still did it, right? It still managed to knock this one out of the park by taking human language, moving it in, chopping it up, moving it around, analyzing it, creating internal models, shifting its data around until it's able to say, oh yeah, here's the clear path towards producing Python scripts that would achieve this goal. That is a lot. You can also do images. Here is the DALL-E system that uses GPT-3, and it takes a text prompt and turns it into an image. DALL-E. So, here's one. A storefront that has the word OpenAI written on it. Look at this. These are images that this system produced. It created these. It took some properties from this language and it comprehended something about them, and it went on to a whole different system that was able to do this sort of creative effort. This is something that the power of certain neural networks these days can handle. And it creates these very convincing images. Like, I believe that there is a place called OpenAI somewhere in wherever these are, like San Francisco or whatever. I know it's not true because I know this is from their website. This is something that the system generated. But it created it from text, right? The exact same cat on the top as a sketch on the bottom. Here's a cat. Here's a sketch of that cat. And they're all a little different too, right? It takes a little bit different approach every time. How about this one? An illustration of a baby daikon radish in a tutu walking a dog. That kind of blows me away. That's pretty wild that it's able to comprehend all this, find this way of producing a cartoonish representation of a radish, put it in a tutu, give it a leash, give it an arm. I'm not even sure how this is done, but I know that it is done computationally by a computer, processing language, and doing all kinds of other stuff on top. So this brings us back around. If I asked GPT-3, design an armchair in the shape of an avocado, and DALL-E was the system I was doing that through, DALL-E doesn't care. DALL-E says, sure, whatever. How many do you want? It just does it. So that's the power of these kinds of algorithms that you're going to be learning, that you're going to be getting into, right? You won't be building GPT-3. What you'll be building is a few different things that touch on the surface of the world of GPT-3. So, GPT-3, it's currently only available in limited capacity through the web API of this particular group, the OpenAI group. And it's mostly for like research or app development and stuff right now. So we're not going to use this, but it's an example of like the hardest, cutting edge, highest end version of sort of the fun toy stuff that we'll be playing with in the course. But I ask you, please keep an eye on GPT-3. Just if you run into it, let me know. Just show me anything you find out in the wild, because this stuff is crazy and it's fun. So, well, it's beyond fun. It's almost intimidating. So that's an open question, right? Okay. So anyway, welcome. I hope this has set the stage for you to sort of get at what space we'll be moving around in. We're going to learn some interesting, fun ways to mess around with language on the computer, and we're hopefully through that you're going to develop a better understanding of the ins and outs of these methods, and hopefully in the end you'll also find a way to enjoy applying this to something that you yourself are interested in, even if that's just for the sake of jokes. I promise that's valid for your project. So, yeah, welcome to the course. Now, I'd like to leave you with a sort of a final thought to sort of chew on. May not come up in any discussions currently, but hopefully it prompts your own. So, final thought. GPT-3 is an exciting and powerful piece of technology. But do you think we should be concerned about its capabilities? How might the system be abused or become compromised? What good will come from it? What is the balance? All right. Thanks much. Take care.